at the end of the last session, and because we don't have Namita and Neeraj as yet, as far as I see, they're probably
No,
not
they
here
haven't
yet.
come yet.
So we will take that up right at the end. So Senthil, if you're ready, we can jump straight into mensuration.
Okay, sure. Is it audible?
Yes.
Okay. With the mensuration, it is sometimes it's very we have been doing this mensuration for a long time even in classes from grade 1 to without unknowingly, like how many say you bring mats, and then so we used to sit on the floor in our schools, and then like so you bring mats and then arrange in ways whichever you want to sit. If there are like 10 children in the class, you want to sit in a circle, that's one way, and probably in a straight line or in 2 rows or in 3 rows, however you sit. How do you sit in such a way that all rows are full? So that could be one way of looking at, say, eventually without saying the word factors, like how can you say 8 people can sit in one long row of one person each in that row, or it could be like 2 rows of 4, like that. So that is one way of it was recently a teacher was also helping in multiplication, and she would always start with the multiplication as also as a box where how many small boxes are there, if it is like 2 times 4 or 3 times 4. So moving on from there, I sort of feel you can actually have tiles in the class, or if there is a classroom which have tiles, you can use that as a clear example of children's walking on the floor and then checking how many squares on one side, how many squares on the other side, and what are the total number of squares. And many children intuitively will be able to say it is they would start counting each row, but after 2 rows they would know, yeah, it's a 5 times tables which is moving from 5, 10, 15, 20 for a square of like say 5 by 4. So but many books start with a triangle. I sort of tend intuitively that it's better to start with a rectangle, because in many ways it's very easy for children to see the length into the breadth. And so move on, and we'll see that we start with the rectangle itself, and but always start with a whole number, so for 4 feet by 2 feet, and which means that you look at how many are there in the length, and then you start counting each one by one and end up having 8 feet and 8 squares. And how many different ways can it be arranged? Will the area change if it is 8 feet by 1 feet, or will the area change if it is 16 feet by half feet? And all those discussions can happen in the class, and sometimes they would feel, oh, it's quite long, and so it will be big. And with all these things, if we could clearly see, there are ways in which if you give them a set of cards and ask them to arrange, how do they arrange these different cards? Are the cards increasing the number of cards if you arrange in a different way, or the cards are same? All these explorations can happen with the children. So typically they should literally view it as a 2-dimensional thing without we using the word 2-dimension for this. So it is they should see it as a plane. They should see it in a floor, and that is more important, or in a wall. That is very important. And if it is 360 square units, they should mean it as square units, because that is very important. Even when we move on to circle later on, we are still talking in square units, even in the area of the circle. So 360 square units, how many different ways they could feel it? It could be like 10 times 36 and 20 times 18, or 5 times 72. It could be various things, all these options, but they should literally see it as 1 foot by 1 foot. That is the key thing. And many times when we write 10 square feet or 10 feet square, there is a possible confusion of is it 10 square or 100, or, and the thing is, when we introduce this as 10 feet square is not yet introduced in that age. Its exponents comes much later. So most of the teachers who are handling it in the class would know that, oh, that's a term I haven't introduced yet. So instead of writing, so you write 10 and then SQ dot feet. That's much better. 10 square feet. And area of a right triangle, we start with a rectangle and then move to a rectangle can be seen as like two right triangles which are of same congruent itself. And in that, it's just half the area of the rectangle. So here, the terminologies can mix and match between the length, breadth, and the height. So length and breadth here for the rectangle would become the base and the height for the triangle. And once they get confident about these whole numbers, area of a rectangle with 4 feet by 3 feet, they can slowly move on to 4.5 feet by 3 1/3 feet. And but they can still draw it on the book and then see how many full square feet are there, and then how many halves are there, how many 1/3 are there. There's a and what makes by this time they would have also been introduced to the fractions. So what does one whole mean when you have to use all three options, like a half, a 1/3, and 1/6? If you have to use, how is that different? So in the letter here, like area of a rectangle, there's a mistake, I guess, like in 12 square feet, and then 3 half feet and 4 1/3 feet and 1/2 feet and 1/3. It should be like that, so that the 1/3 and 1/6 would make 1/2, and then another half would make it as one whole feet, and then the others will add up to 15 square feet. Yeah, but if you just do it by your own, you should be able to get that. And you can still make it with area of a rectangle of 2 2/3 feet by 3 1/4 feet. So even this, if you start drawing, but you don't need to stick on to this concrete drawing forever. It's probably for 2 days you stick with the drawing, they will get the hang of it, and then you have to just multiply these two fractions to get the area, is what they would understand. And once they get confident, you move on without the drawing. So just 1 day or 2 days for the first one, and the second one, if you take a longer time for them to literally understand these things, then we don't need to slow down. Then later on, it can be picked up very quickly. Yeah. Next. Here, this is from rectangle, we move on to the next one, is the parallelogram. And the moment anybody see the parallelogram, initially, like always we start with the estimating what is the area of this. Is it more than rectangle, less than rectangle? Is it equal to rectangle? And many children would start estimating intuitively that it is more than rectangle because it seems to be longer on the base. And but if you show them a set of cards, this is something which I've learned recently also, like probably 2 years back, and then there you arrange a set of cards of a deck of cards with 52 cards in that, and you slowly push them to one side by tapping it, and then you can see all the cards are still moving, slanting, but it is still the number of cards didn't change. So the number of cards is same, which means that on the side when we view it, all the cards are intact, which is same as 52 cards now. It's just arrangement is different. So between the rectangle and parallelogram, for rectangle, it was the area was base into length, which is like base into height, we can say, which is length into breadth. But here, instead of calling it length into breadth, if you say base into height, parallelograms, it remains the same. It is not the product of the sides, but it is the height versus the base. And that is important to remember. But that can also be looked at as you can cut the corners so that the slant part becomes two triangles, and then there is one rectangle part inside, and the two triangles can merge to make another rectangle, which would be exactly like the first rectangle. So that's also a possibility. And if you look at any triangle, area is like half of base into height, which is even because the apex point can be like tilted anywhere. It's basically this shearing of the whole area and then stretching it a bit. That's what is happening here. Because the height and the base is not changing, the area will not change, however the triangle is. That is key to understand. Yeah. And we can look at how in a trapezium or trapezoid, so how do we look at what is the area? And this should be explored with the children, the formula for trapezium. And you can tell them that here are these, you can look at, use the formula for the triangle, rectangle, and how do you get the area of the trapezium. Here there are two different ways of three different ways which are shown here, which is on the trapezium, there is a height and there are two elements of the base. There are two different bases which is available. One is A and the other one is B. Both are parallel, and that's the key thing to use a rectangle here. So if you slice it across the diagonal, then what happens is you get two triangles, which is the base with A and B, but both have the height similar. So it is two triangles, so half base into height, but base being two different things, like A for one triangle and B for another triangle, it adds up to half A plus B into height. And whereas the other one is like you can just take out a triangle and you can have the remaining parallelogram where A and B minus A would be the base of the triangle, whereas the other one would become A as a parallelogram side, and base and height is remains same. That is one way of looking at it. Or you cut it in such a way that both base becomes A plus B and height becomes half. There are various ways of doing it. It's not just one simple way, but all of them are elegant in many ways. So once we figure out these things along with children, then this becomes a formula which is derived by them itself. And that journey or the discovery of the formula is very important.
So do you physically take these pieces of paper and then try and work it out?
Yes, we mark it and then ask them to first intuitively draw it in the sheet and then see how you can fit it. And so that you color code it and then see how you want to shape it, or cut the sheet from the chart paper and then place it in such a way that you understand what is the evolving shape out of it. Can you see a parallelogram and a triangle from this trapezium itself? Can you see a long parallelogram if you cut it in such a way that if you cut exactly in the middle of this triangle, the first trapezium horizontally, then it can be just rotated and placed in such a way that A plus B becomes the base. So, and then you see the parallelogram coming out. And so all these things can be explored with the children, and we should guide at least one of the shapes along with the class. And most likely one of the ideas would come from children itself. It's just that we need to bring it to a larger awareness for the class. That's enough.
Okay.
And this is something which we have seen with the Bama's presentation also. We always start with measuring. It's the most important thing between in the circle is to find the ratio of the diameter to the circumference. And once we find that ratio, to find that ratio, that we start with an activity of the whole class goes out, start measuring the circumference of the school van and a bullock cart and a plate and all these things, the lunch plate and some bangles. And so this is an activity which they keep doing, and one group is going to measure the diameter of all these things, and we start listing them down. And what is the ratio between the diameter and the circumference? Once we figure out that, and what eventually becomes is we find the ratio pi. And the moment we find the ratio pi, it is also in the class, it becomes mesmerizing to see however big the circle, the ratio doesn't change, is fascinating for some children with all the innocence remaining around 11 years and 10 years. It's really nice to see them have a feel for it. And once we find that, how do we look at finding the circumference? Once how do you cut these things, and can you make it as a triangle of the shape itself? How do you relate the circle to whatever we have learned so far, which is a triangle and the rectangle? The first one is an example of how to visualize it as a triangle, and whereas the second one is a rectangle thing. The second one is something which almost all classes would do, the second experiment, where you start cutting with the through the diameter and then make it 1/4, 1/8, 1/16. And when we have 16 pieces, 8 pieces goes up, 8 pieces goes down, and then we find this. And we still say there is a mild issue here because of the curves, but if we cut infinitely many pieces, it would end up being a rectangle. And once they get that, then it is looking like a, how many different squares can you see here? And that would end up as pi times r squares into the pi r square time the small square units is what they would see is something they can easily relate to. Once they, I think we have to slow down on the circle also, because it's sort of changes the intuition itself, and to imagine small square inside is critical. So we take the help of the rectangle and the triangle and figure this out. And when we look at in grade 8, probably the volume starts. And when we start with this, sometimes what happens is it could seem as a daunting task to have so many formulas, and how do we teach all these formulas? There are these rectangular prisms like blocks, and then eventually you will also start seeing pyramids and all those things like cones. How are we going to memorize all these formulas? It's very simple, like the way we start with a rectangular area, uh, which is now area of the base is very key. And once we have area of the base, we can start looking at how many layers are there for the volume. So all these things are like small planes, and all these planes are like arranged in one on top of the other as a stack. And the moment we imagine all these things, then we can look at if so many tiles are there in the room, and if we are going to have these tiles as with some height to the thickness also, and it would eventually become the volume of the whole class. And what would be the volume of, say, if there are 8 by 8 squares, 64 squares, and if you just raise the whole thing by 1 feet, and what would be, how much water would it contain, and all those things, it could be a nice exploration. For this also, you start by having a sheet of 10 by 10 square, like 10 centimeter square sheet, and then ask them to cut out the last corner pieces. The 4 corner pieces, once you cut out, you get 9 by 9. But the thing is, it's only the corner is cut out. It would turn out to be a flap from the sides. So on the length sides also, you turn the flap, and on the breadth sides also, you turn the flap up. It will look like a tray, and you can have certain volume in it. And if you cut 2 squares on each side, and then on the corners, and if you fold up, the height is going to increase by 2 feet, but the area is going to decrease. And we can have an exploration in the class, like what do you think would be the optimal volume or the maximum volume when you keep reducing, because the height is going to keep increasing but the area would decrease. Where do you think would be the optimal thing? And this could be a nice exploration for them to see. You can have a cup of, if you start with something like a chart paper, you can have this ragi being poured into it. You can understand what is happening here. And slowly, when we understand like where the area is increasing or decreasing, then you can also go and look at how the formula would arrive, and they would be able to explain that it's area into height is what the formula teacher. And then like, so if the base is rectangle or triangle or circle, it's all the area which we have found out so far, and into the height is going to be the volume of all these prisms. And that is important for them to visualize it. And you can play around with all these shapes also by making a net for these things, then suddenly these nets would become so while making the nets, it's also easy for us to see what is the surface area for these things, and which would come later, but it's easier to relate to these things. And it's very important, just like we have uh, spent time to make sure that they visualized in the two dimension as a plane, here they have to visualize in a cubic form, and that is very important. The 3D form should be visualized for them. That's so key. And this is something which we have seen in the ratio thing also, the pyramids. And so here, the difference between the prism and the pyramid is the top portion is converging to one single point. And what happens here with the volume? And there is a nice experiment for the cylinder and cone. You can definitely use bring, if you have a cylinder and a cone, most schools probably would have, and it can be for the children to play around with sand or some powders or all those things, or liquid measures. It could be just a flowing measure, and you start pouring into the cylinder to understand what's the volume. But to look at it as a square is a very interesting thing, which we have done this kind of a. So you assume that you are in a square, in a room where the length and breadth of the floor is same as the height of the room also. If you have such a room, and then suddenly you just uh, consider or assume the room as a tent itself. On four sides it's coming, but the apex point is just in the middle of the room. That's the figure on the middle. So from there, what is the volume of this particular tent, like a pyramid form with a square base where the height is also same as the sides of the square? What is the volume? Many children would say it's half or a quarter or anything like that, but assume that we are going to shift the apex of that center part to towards one of the corners, so that in one corner it becomes a right angle. On the So if you see that orange figure, you see the right angle towards the right side of the figure, but the other two angles are, there is, it's a right angle with the isosceles right triangle, which we can see with the base and the height being the same, and it has a hypotenuse. Now this hypotenuse and the other hypotenuse is also same, and there is a larger side which is on the third one. So once we make this, you open this flap and open this net, and then see how the net is going to come. Children are going to just visualize these things and draw the net. And once they draw the net, they form a solid shape out of it, and then connect all the nets, fold it, and then stick it. Once three nets are formed, then it is very interesting to see how a cube can be formed from that. It's fascinating because on the look of it, it's very difficult to understand how these three are going to get formed into one particular cube. And the moment they see all these three pieces are going to form a cube, we can understand it's always the one third. The only thing is here is the height and the base is common, then it's one third exactly. If the height is going to be differing, probably that also would work, is what I think. It's all one third still. Uh, yeah. So for the formula here, if we look at the previous slide, the volume of the prisms, it's basically volume is base into height. Now, when we have understood in the pyramids that it's one third, so volume of base into height is basically the volume of that particular shape into one third is what for the pyramids of circular and square or triangular base, it's always the one third. And so for the cone also, it's one third of the cylinder. And so in that way, it's not so difficult to memorize these formulas. Yeah, once we understood, once we spend a lot of time on the square pyramid, then the circle becomes the cone, and that's not so difficult. Ratio, this is something fascinating. If possible, the teacher should bring these things to class and then show them how to measure these things. And because from the cone, once we measure with the cone, we understood that it's 3 times of the cone's volume. But it would be very interesting to see what is happening with the sphere. So how much is pending? So this is the Archimedes' ratio, where once we have the cone and the sphere and the cylinder, all the height is also same of the cylinder, cone, and the sphere's radius and the diameter. Everything is similar. That's very important for this to be understood. And we start pouring water into. So you can also place the sphere directly into the cylinder, and you start pouring water into it. It fits exactly 1 cone's volume, which if you remove the cylinder, if you remove the sphere from the cylinder and then start pouring, it fills into 3 cups of the cone. So from that, it's very easy for us to understand what is the volume of the sphere. Once they go through these exercises, we can allow the children to understand like what is the volume of the sphere itself. Though it seems like 2/3 of a cylinder, because of the it's 4/3 pi r cube is also it ends up as a formula, right? And so it is very nice to slowly relate to these things. Take time and do it. So then they don't need to memorize the formula. So for the cone, it's 1/3 of the cylinder. For the volume, for the sphere, it's 2/3 of the cylinder. Yeah, and it's just need to be done slowly, and then a lot of practice can come later. Yeah, this is something which we have done in the class itself. There are wonderful videos for this surface area of a square. For all the other things, the surface area is very easy. When we open the net itself, we'll be able to understand the surface area. But for a sphere, it's not so easy. There is a light and shadow activity, which they say, where you float a ball and then have a light from the top and see there is one side. So if you have to take out so wherever the light is falling, you will see the shadow on the below. So that is one circle you will see. And if you there would be places where the light has not fallen yet, so you need to start showing those sides also. From the side, from the bottom, if you have the light, then there is a shadow on the top. That becomes another circle. And there are still places which there is not enough light which is falling. So it's an interesting activity for them to visualize it and then see it. There are wonderful videos which are available on the light thing itself. Where is it increasing and how is it increasing the surface area? That would be very nice for them to see it. And for the easiest thing is like a tennis ball or an orange or the Mosambik, where you peel off all those things and then draw the exact circles and start placing them on the sheet itself. And it just forms into 4 circles. It's amazing to see it, because it's not intuitively, it's not easy to see this shape. But once you start arranging, it just fits perfectly into it. And once you give this as a task to children, they would come with smallest of the shapes to perfectly fit in the circle. And that would be fascinating for children to understand this. Yeah, this cone is also something which we can, because it's easier when we buy these cone ice creams these days. It comes with a paper also on it, or you have these cone cups available, or uh, you can make these cone also along with the class itself to fold in however degrees you want, in different heights and all those things. Once you have them, you cut it, open it, and then start measuring the angle and area itself. So here, then they can also relate it to the ratio between the full circle and what is the central angle here of the cone, and it will be that ratio is what is going to be like r/k. So it will be interesting for them to see that. But the thing is, here the slant height of the cone becomes the radius itself. And then so the radius changes. So the circumference of the cone is the slant height into the central angle. So central angle by 360. It's interesting for them to see it. But the thing is, the the mouth of the cone has a different radius. The slant height becomes the radius of the cone itself. So there are two different circles which they have to see it, and they'll find the surface area of this. Yeah, sometimes you have the mouth, or sometimes it is without the mouth. So you can have these things. Yeah, but it's just that slight push for them to understand what is the radius of this cone. Most of them would end up saying it's the mouth. What is if it is like 5 centimeter wide, it's the 5 centimeter wide cone or something like that. But once they cut open and then see, then they understand, oh, that's not the radius. The radius is something else. Yeah.
Very nice. Okay, okay. Okay, super. Thank you, Sandhya. Are there any questions on Sandhya? Is making nets a part of the CBSE curriculum? Can somebody help me with that? Any
Yeah,
of the
it is,
participants?
Ramesh.
It is,
It
okay,
is. It is.
okay,
It's
okay,
either eighth or ninth, I think they do. Part of the
okay.
curriculum, yeah.
All right, okay. Thank you, ma'am.
But they also say around eighth and ninth, the CBSE schools, I don't know if they do Platonic solids and the Euclidean solids and all, but it'll be nice to have that experience of
Yeah.
how to make nets for a Platonic solids, and yeah, it would be fascinating.
Yeah, yeah.
They don't have separately Platonic and Euclidean. They don't. They just have it as, yeah, it'll be nice.
Yeah. Ruchi says, yes, there is, and it starts from fifth and goes all the way to eighth, it seems, making nets. Okay, great. As long as making nets is there, it is wonderful.
I think it is. It also, when Ruchi says fifth grade it starts, it also brings back to that which we have been talking about, like a 3-year plan, like where you introduce a topic in 1 year and then consolidate the next year and then really master it in the third year or the fourth year. It sits very well in that aspect as
Right, right. Yeah, yeah.
well.
Okay, super. Thank you. Now, when the topic we wanted to take up is a pedagogical idea, which you just named it intuition first. Uh, but just let's go back to what we tried to do in mensuration. Now, in mensuration, we can always say that area of a rectangle is length into breadth, area of a parallelogram equal to base into height, area of a trapezium is equal to half into height into the two sides A and B. Area of a triangle is half into base into height. The area of the surface area of a sphere could be something. So now if we develop the topic like that, and then we get into volume, we get into pi r squared h and length into breadth into height and 1 by 3 pi r squared h and all kinds of things. Before we know it, the topic of mensuration, we are left with 20, 30, 40 formulas. These 20, 30, 40 formulas stand as disjointed pieces in the head of a child. They stand as disjointed pieces in the head of a child simply because the connecting mechanism which is there underneath that, if it is formulas, what happens is you take the formula as a given and there is no connecting mechanism at all. Intuition first really is about how do we create that connecting mechanism? How do we create a mechanism by which we ask some questions in a class and the child or the children are able to start answering some of those questions? We don't obviously ask a question like, what do you think is the surface area of a sphere? That's not a question to, it's not a fair question to ask in the first place. And in any case, the right answer is not likely to come out unless somebody had Googled it or seen it somewhere else, right? So what we really try to do is we start asking some exploratory questions, start asking, what do you think will happen here? What this might lead us to? Where do you think we will land? Okay. And we start exploring that as a classroom is really where we build the intuition. When we say intuition, what we want to build is before we get into any topic, we start off with a certain story, and that story has got an open end to it. Open end in the sense there is a question which is there in that particular story which is embedded. And then together as a class, we develop the question by trying to find different answers to that particular question. And as we are exploring and finding more answers to the question, we start noting down those points. When we start noting down those points, from that process of discovering it, from the process of intuition, the solution emerges. Now, when a solution emerges from intuition and from the process of discovery, what happens is the solution is owned by the class. The solution is no longer, if you had told somebody that the volume of a cone equal to 1 by 3 pi r squared h, then there is no solution which is owned by the class. It was just given by the teacher to the class, and the class passively accepts that because the teacher is at a higher power than the students, and the students passively accept it from the teacher. Okay, and that is an important aspect generally to break in mathematics and in life itself more generally. Okay, so with that, we will get started. So as far as we are concerned, between Bama, Sendil, myself, and many other teachers who we are a part of a group, many of us, we have 2 or 3 very strong convictions, and I wanted to lay that out on the table first. The first one is, if right methods are used, all, okay, it's important to note the word all children are highly capable of learning math well. So as a teacher, okay, it is very, very important that we don't repeat the statement, but we truly internalize it and believe the statement, which is, when a student comes along, I have to have the strong faith as a teacher that this child is capable of learning mathematics and learning mathematics really well. And every child is capable of learning mathematics really well. Now, why is there a gap? The gap is where what happens in the interaction between the teacher and the students. Now, any one of us with a true love for the subject and a love for the children can work wonders. Now, both these pieces are very important. It is not sufficient for us to have a true love for the subject. Of course, the articulation and the communication ability comes in as well in teaching, but it's not just those things. A love for the subject is critically important, but we have to understand that we are not teaching that subject. Okay, adult learners learn very differently from children. As far as adult learners are concerned, adult learners typically go and learn something because they want to enhance their skill. If I want to learn about what is machine learning, I will go to YouTube or Coursera or somewhere, and I will look up various videos on machine learning, and I will carefully understand what that particular teacher is telling me because I need it. It is my requirement to learn machine learning, and therefore I will learn it properly because it is my need. And it's not about the teacher. As long as the teacher is able to explain the concept very well and has a love for the subject, that's fine, well enough. And I don't really care what the person thinks about me or the other way around. Whereas in younger children, it's simply not that. In younger children, always a child will like a subject or rather the child will like the subject where it likes the teacher. You can ask this question randomly to any child, okay? The younger, the better. Go to a third or a fourth grader and just ask them, what's your favorite subject? Okay, and they will give you a subject. And you then ask them, who's your favorite teacher in school? They'll give you a teacher's name. And slowly, without it being like a rapid fire question round or something like that, slowly ask them, which subject does that particular teacher teach? And you will find that very often that subject, the teacher, is one and the same. It's very often it is woven inside. If they like a teacher, they like the subject, because they have not come there saying that, let me learn about mensuration today. They haven't come like that. Unlike the machine learning, let me learn about machine learning is my initiative. A child is not coming with an initiative. The child is coming to learn. I'm not saying the child is coming lazily. The child is coming to, with a curious mind. The child is coming to a class, but the child has not made any, decision in terms of, I want to learn mensuration today. I want to learn algebra or trigonometry or something like that. And it's important that we are able to introduce it in such a way that they like us, and that we are able to give the subject which we are truly in love with. So, which then means all we have to do, okay, is we have to train ourselves. Rather than thinking of it as saying that some children are lazy, some children are good in math, girls are like this, boys are like that, I have this child like that. If you just erase all of that and truly go with the conviction that all the children in my class are highly capable of learning, as long as I use the right methods, I have a love for the subject, and most importantly, I have a love for my children. I know all my children personally and deeply. If all of those conditions are met, okay, it's just a matter of time. Every child will be learning mathematics. Here again, I want to be careful and call it out and say, I'm not saying all children will get 95 on 100 or 100 on 100 on mathematics. We are not saying that. All children are capable of learning mathematics to the extent they can go up to their potential. Okay, so we won't lose the children who have lost, whom we have lost to ideas like math is tough, math is only for these kinds of people, math is only for this, and math is a boring subject. All of those things is what we can make, and they can go up to potential. And that potential for some children might be 50 marks, some children might be 70, some children could be 98, or whatever those numbers are. That doesn't really matter. We have spoken about that in the past as well. Right. So the third point is, how do we is training ourselves, in which case, how do we train ourselves? We've seen this one picture, I think a couple of times in the past as well, where there are three axes to learning mathematics. There is one which is the computational, procedural, formulaic aspect. The computational, procedural, formulaic aspect is like this. How much is x plus y whole squared? It's x squared plus y squared plus 2xy. That is a formula, and we are given a certain procedure to work with, and we will be able to do that. What is the perimeter of or the surface area of a sphere? Then we are given a certain formula, and we can apply that and get it. Okay. How do we divide a very large number by a small number? There is a long division, which is a method which we are given. All of these are computations and procedures. Computations and procedures are very important to get to an answer, but they are not the places where you can create excitement in a class. They are the part which, if we have been able to create enough excitement, enough goodwill with the children, then they will be okay to do the procedure. If procedure is the only thing we are doing with our children, chances are children will get bored and they will be saying that math is boring and move away from that. So the trick is to be able to create enough excitement in a class so that they're getting 40 minutes out of 40 minutes, they're getting 25 minutes of real quality excitement. And when we say excitement, we are talking about thinking excitement. We are not talking about excitement which is off the subject. This is excitement on the subject. Okay, on the topic, on the subject, can we create excitement in a class? And if that is created for 25 minutes, then the 15 minutes of procedure, they'll be quite okay to do that, because it is one of the important aspects in learning mathematics, which is therefore the procedural, the conceptual, how do they come, where do they come, and the problem solving, which is given a certain task, how do I even approach it, how do I go about solving that particular problem. As far as mathematics is concerned, while some of the testing which gets done, okay, is asking a set of questions in a short amount of time, math itself is not about that. Math is not simply about providing short answers, to narrow questions in a limited amount of time. Math is an explorative subject which has to be explored. The beauty of it has to be explored, and the intuitions have to be built, the patterns have to be recognized. Math is a form of thinking. A mathematical thinking is what we want to develop. Within the mathematical thinking, I mean, that part is there. And then there are certain elements which are the procedural, computational, formulaic aspects which are developed, which are those specific skills, and we should be in a position to integrate the two in terms of our mathematical thinking and the procedural and the skill aspect of mathematics itself. Okay, so now this is a question, by the way, which was asked. There is a test which is called the PISA test. Okay, the PISA test was administered, and a lot of Indian kids also took it about, I think, 4 or 5 years back. The question is as straightforward and simple as this. Mount Fuji, which is a famous dormant volcano and a big mountain where people climb that particular mountain. Mount Fuji is open to public only for a few days, from the 1st of July all the way to, say, the 30th of August or 27th of August. Okay. And in a year, about 200,000 people land in that particular place to trek and climb Mount Fuji, which is in Japan. How many people are climbing that on an average each day? Now, this is a question which was asked in a PISA test, okay? And a very, very large proportion, I'm not asking you to compute it here, a very large proportion of children from India really failed on this particular thing. So we have to ask ourselves the question, why is that so? If all our children are doing all the classwork properly, homework properly, they're scoring 100 marks and 90 marks and everything else, why is it when a question is posed like this, that one is not able to find the correct answer for this? The reason is, once we are told a certain path, and then we are given a question which asks us to go down the exact same path, we know how to travel the path and get to the door or get to the answer. But the moment it is given or presented in a way which is a bit different from the way we are used to, we don't know how to approach it, because what we have become is we have become a slave of the process and the procedure. So we no longer have the ability to take this as a problem, accept it as a problem, receive it, understand it as a problem, apply the conceptual thinking, which I already have, not the formulas, the conceptual thinking I have. How do I approach a problem like this? Are we talking about how many people on an average climb during the period when this particular window is open, from July 1st to August 27th? Or are they asking me for the whole year of 365 days, how many? Is it 200,000 divided by 365? Is it 200,000 divided by some 60 odd days? Or is it something else they are asking? Or is it 200,000 people are climbing every day? Or is it for the whole year? So now think about that particular problem and understand it conceptually, and then apply the right procedure to get to the answer. If you're taught only the procedure, what happens is we need to give a question which doesn't call for the conceptual thinking. As long as it's a procedural question, the child will be able to solve it again and again and again, as many times, as many problems, as big a problem as possible. But the moment it is given a problem that is a little off from the main way of asking that particular question, the child might struggle. That is because the conceptual thinking has not, or the intuition on how to approach a problem has not been properly done. So if we go back to a math class and typically look at it, what happens in our math class? Okay, in a math class, what we want is we want a math class which raises curiosity. Okay, it has to be like a thriller or a suspense movie, not the excitement in words, the excitement which gets developed when a certain problem is posed. Okay, there is something very curious about the problem which is posed, and the excitement gets created there. Once the excitement gets created, then the process of discovery starts. And that itself is the fun we are talking about. We are not talking about fun by saying in the younger classes, of course, using manipulatives could be fun, like cutting papers and painting and coloring and all of that. In the higher classes, the fun is really about the fun which happens inside our head. It is not the fun. We can't use colors anymore and crayons and color. All of that is gone. But how do we retain the fun? The fun is really inside the head, because the fun which comes out of the curiosity, the process of discovery, and the fun and the practical aspect of all of that get integrated and woven in. However, if a math class looks anything like this is very, very likely that this math class is not going to be accepted by the students who have not come in saying that I want to learn algebra. They've just come into a class. We think they need to learn algebra. That's very different from the machine learning example I took, where I want to learn machine learning and I went and picked it up from the internet. In the case of children, they are not coming to learn algebra. They are just coming to class to fulfill a certain curiosity. And if that demand for curiosity and discovery, the process of discovery is not effectively met, then the class can turn very boring. And this class with lots of formulas and things on the board will get rejected by the class.
Just one thing, if I can add, Ramesh, I don't know if I
Yes,
can
of course.
interrupt the flow.
Sure,
So
go ahead.
here we were doing this geometry in the class where we have been constructing different shapes, and once we have constructed like from rectangle, parallelogram, and a kite shape. I don't know what do we call a kite shape, like a rhombus, where one of the diagonals is extended. So it's sort of a diamond where one of the triangles is extended.
Yeah, so the two adjacent sides are same. The top two adjacent sides are the same. Bottom two that we call as kite.
Kite.
Yeah.
I don't recollect what is the shape name, but it's very interesting. So once we have done these things, it's called a kite. Yeah, that's what we also called it. And once we have done this, what happens is like we started drawing many different shapes. And is it audible?
Yes.
Okay. And we had this. So there is a trapezium which we drew, and we started marking the different midpoints of all these sides, and we asked the children, what do you think would be the shape which would eventually come out of it when you start marking the midpoints? And what happens when you start marking the midpoints of the further inside figure? So it keeps going. Okay, so when you start with a rectangle, start marking the midpoints, what would be the next figure? And then when you start again from the midpoints of that figure, what happens to the next figure? And what happens when you start with a square and start marking it? What happens when you start with a rhombus and start marking it? But none of these things, they're not going to draw at all. But the drawing happens in their mind, and they are very engaged. And what happens is you draw all these figures and give them numbers. So they're not going to scream in the class, but they have to show it with their fingers. So the class, you can see different numbers coming from different children, but they are very engaged. So it moves between a rhombus and a square, rhombus and a square. And so it's nice for them to be in this exercise. And there is a pattern to it. So slowly they figure out the moment any shape ends up in a rectangle, it is going to form a further similar pattern only. And this is in many ways it is very important, because in younger years, like you start with a lot of manipulators. Now if you use a lot of manipulators in your middle school and high school, it is going to be detrimental for the children. So the movement is physical in the younger grades, the movement is in the mind in the middle school and above. So we should make the movement happening. That's what I understood from the previous slide. So otherwise, what happens if we just deal with the formulas, there won't be any movement which is happening. It becomes very draining for them. Yeah.
I think that's a very nice way to describe it. I think in the younger classes, the physical manipulatives is where the when the objects are coming and two things are getting meshed into each other and then they are forming into a whole. It's all a beautiful, process of discovery when these things are happening. There is a type of fraction rods called Cuisenaire rods, where we can see arrange those rods and then suddenly it becomes 1 and 2, and it's a very, very interesting exercise for a fifth grader, fourth graders and all that. But as they come to seventh and eighth grade, the same movement has to happen, but it is not happening externally. The same movement has to happen internally. If it becomes a passive recipient of formulas, if the mind has just become a very passive recipient, it's just a matter of time before that mind switches off and says, what the hell am I doing? Okay. And that is, I think somebody mentioned it yesterday. I think Sendil, you mentioned it yesterday, in some other session we had, where he was saying that many times children come back and ask this question, saying that what is the practical value of learning, let us say, trigonometry, or the practical value of learning algebra? They never ask the question when it comes to playing football. What is the practical value of playing football? The very fact that somebody is asking you what is the practical value of learning something means they're finding it boring, and they're saying, at least give me some reason why I should continue. Okay, because it is not exciting my soul. Will it at least excite my career and job and everything else, and at least give me a practical thing? Because it's not a soulful experience I'm going through. At least let me have some reason why I'm going through this pain. Okay, and that is when the question that what is the practical value really comes up. Yeah, so moving on, in a traditional math class, therefore what happens is that the children first learn what the topic is. Okay, and the topic, without any exploration, the topic is introduced like that. So saying that today we can talk about the volume of solids, and then we get down to saying that there are different types of solids. There's a kind of solid called a cuboid. There is another type of called, it could be a hexagonal prism, it could be a cone or a sphere or hemisphere or any of those things. They learn about all of those things, and then they get straight down to the formulas. Once they get down to the formulas, the next step is, whenever you see of and this one and cone, whenever it says cone, remember 1/3. Okay, whenever it's not a cone, it says a cylinder, there is no 1/3 there. This is all shortcuts and tricks which are taught. And then we start solving known problems, and we repeat solving those known problems repetitively, so we become efficient in doing that. We don't become proficient in the field of mathematics. So what we become is, we become very efficient in doing the same problem, or a similar kind of problem, or a similar looking problem. The PISA test on Mount Fuji was not a similar looking problem, and hence the struggle. They learn how to do it efficiently, and then if the problem is posed differently, like the PISA problem, what happens is there is a struggle. And that struggle is a problematic struggle. However, if you look at real life, any one of us, what are the math problems we solve today? Not the math problems we solve in a classroom. What are the real life math problems we solve? And every one of those math problems is an unknown problem. In the sense, it doesn't come with a label saying that, please apply the concepts you learned in mensuration to tell me whether how many buckets of water should be used to fill up this water tank. It doesn't say, please use your idea of addition and division to know whether your budget and subtraction and addition and everything, whether you will be able to match your monthly budget. So as soon as there is a monthly budget, we know that it is about addition, multiplication, division, and all that. And it kind of flows like that. So real life is only filled with that. And therefore, it is important that we get down to the process of curiosity and discovery, which is what? It is where we start with a problem. It could be a problem on measurement, which we spoke about today. It could be a problem on exponents, which Bama had spoken about some time back. It could be a problem on prime number, which I had spoken about some time back. Okay, we will take those three examples. As a class, we have to explore how to solve a problem of that particular nature. And for us, for an exploration to stay an exploration, it's critical that answers don't come in the way. our knowledge and our answers and the fact that we know the answers can sometimes come in the way of quality thinking in a classroom. Okay, so it is important to hold that back, that we know the answer is not enough. So we want the class to discover that particular answer, and we want them to truly discover and not take it from our mouth and say that teacher told me so and that's okay. And then wherever it is possible to engage in an activity, we can engage in an activity. Now let's take some 2-3 examples here to drive home the point or understand the point of discovery and intuition. When we looked at measurement, for instance, okay, in measurement, one can very easily get started. After some amount of measurement, we can introduce something called, there are standard measures of measurement. Standard measures of measurement are like inches, feet, and mile and stuff like that, or it could be centimeters, meters, and kilometers, or it could be any other standardized measure. And these are this is called the metric system, this is called some other system, and so on and so forth. But in doing that, what happens is there is no intuition which is built, and there is no discovery for sure. Now, what did we talk about in measurement is simply this, that we want all the children to use their feet to measure how many feet is this, length of a classroom. There is a child who says it's 21, there is another child who's saying it is 18, and the third child is saying it's 25. Then we start off by saying, who's lying? Because the room is not changing size. Okay, we can all see that the size of the room is the same. Somebody is saying 18, someone is saying 21, and someone is saying 25. What, two of you are lying and one is saying the truth, or maybe all three of you are lying. Which one is lying? Then all of them will shout and say, no, none of us is lying. It's exactly like that. You say, okay, go and measure it one more time. So when we do all that, when we measure it one more time, again, the answer is coming the same way. And you ask them, why? Why are the answers different? What is going on here? Then what happens is, it is the same idea. The final answer is not very different. The final answer is what? Standardization, right? The human feet is not standardized, whereas a foot or a meter tape is standardized. It's the same answer finally we come to. But the route we took is very important. We didn't give the answer away. We allowed the class to discover that particular answer. Similarly, when it comes to, let's say, exponents, right? We spoke about fractal tree. Here, we are not even beginning to talk about what is happening here. We just draw a line and then we say, okay, we split this tree into two and each line will be half the length. And then we split it into two, half the length, split it into two and half the length. At some point in time, we start counting the number of branches. We start counting the length of each of those little branches. And we find that the entire idea of exponents flows from a fractal tree. Again, this is a way by which we start with an intuition and get into the discovery, and through the process of asking a question or building something, then the discovery and the intuition and everything happens. Or in prime numbers, if you recall what we were saying in prime numbers, or one of the things on factors is we were saying that how many different rectangles can we make if you have 24 pebbles? Okay, if we break the class into 3 groups and say, can you make a rectangle? The only condition is all of you will have to make a different rectangle. There is a group which would have made 6, 6, 6, 6, making it 24. Another group would have made 8, 8, 8, making it 24. Another group would have made 12 and 12, making it 20, and so on. So there are different groups. Then we start exploring and asking the question, why is it not possible to do it for 17 and 19? And it's not, it is an odd number. The usual question now, the answer which comes from a class after a little bit of time is it's an odd number. Then we say, okay, what about 15? 15 works. So there is something so again, what we are coming to is, can we build an intuition through the open-ended questioning and the discovery process? That's it. So if we are able to build the intuition through the process of open-ended questioning and the discovery as a class, and we obviously have to be a bit careful in class management that the discovery is not always happening with only 2 children. The class is able to discover as a group. Those are slightly different aspects which all of us as teachers know. And then the class builds an intuition around it, and the class comes out with an answer. That answer will stick in the minds of all the children in the class, and it will stick for good. Okay. A few things we have to remember. One is, of course, the process of discovery is fun. The place which is difficult for us as adults to take is the second point, which is cognitive struggle is good. We as teachers think that the easier a problem is, children will like it. All children like a problem which is testing their boundaries. As long as the child is in a non-judgmental environment, okay, if the judgment environment is judgmental, the child will like to stay within the circle of her knowledge. If a child is in a non-judgmental environment, she will want to explore things which is on the boundary of her knowledge. I don't know it yet, but I think I can solve it. That is the place. Okay, I know it. Okay, is a certain kind of mindset. I simply can't solve it. That is too difficult sometimes. Okay, but what we want is to try and get to that place, because that is the place when you're testing the boundary of knowledge of a child is where the cognitive struggle happens. The cognitive struggle is really the fun and the practical aspect we are talking about, or the fun part of it is really the cognitive struggle. The cognitive struggle can be really fun if it's a non-judgmental environment, because the moment the discovery happens, there's a tremendous satisfaction which comes through. Once it is discovered, that satisfaction is so good that it was worth all the cognitive struggle. Okay, and the cognitive struggle, even if the discovery doesn't happen, as long as the cognitive struggle is not judged, it's fine. It still continues like that, right? So this knowledge, which is acquired through the process of actually discovering and going through the cognitive struggle and coming to a certain answer, right or wrong is not important. If that were to happen in every child, okay, that is what math is all about. This is the soulful part of mathematics itself, the discovery and the intuition which gets built, and that is at the soul of it. The formulas, process, procedures are important for the skill. And this is important for developing a mathematical thinking, which is there, should be there in a child. Because once we have taught them how to think mathematics, you pretty much taught them how to fish. You're no longer feeding them fish, which is the formula, you've taught them how to fish. Okay, so when we say intuition first, concept next, and formula last, okay, few things to remember are: don't give away the answer before building intuition. That's it. There's nothing more to it. All we have to say is, am I telling them something and they're going to receive it from me because I'm telling them? Okay, which means they are accepting your authority as a teacher. That is not what we want. We want a society, we want children to be thinking on their own. And for that, they have to figure out what it is. And we will be there along the way. Because the moment we give away an answer or jump into a procedure, the entire process of discovery, intuition, learning, and everything is completely gone. Okay. And it doesn't lead to any kind of exploration or a curious mindset. And when faced with a problem like the previous PISA test we were talking about, the child really doesn't know how to do. Okay. Now, in intuition first, okay, let's take one example. How many squares are there in a chessboard? Can you just type it out in your chat? $64. Okay. Now we ask the children, okay, how many squares are there in a chessboard? And they will say 64, exactly the same way as Anupama, right? Yeah, Anupama has said. And then he asked them, is that so? Are there more squares than 64? Suvarna, Lalita, as well as Anupama, isn't there more than 64 squares? Yes. There's the whole board itself is a square, right? So that makes it at least 65. You can make 2 by 2, 4 by 4. So as an adult, we already know. But imagine taking this problem and developing it. Okay. When we take this problem and develop this entire problem, first we start off by saying, okay, 64 squares. And here the trick is this. We don't tell them, what about these 2 by 2 squares? Then we are giving away the answer. Then we are giving away our knowledge. We just ask them the question saying that, are there any other squares which are there? If the class is still not able to find it, just get it down to saying that, what about the whole board itself? That's a square, right? Okay. Now we have jumped from 1 by 1 to 8 by 8 square. And then somebody will say, no, there is a square inside, and they will draw it. They'll say, okay, that is a good square as well. So how many of those are there? Those are, and as we keep going on, what we will realize is in a chessboard, there are not just 64, there are humongously large number of squares which are there. There are 1 by 1 squares, 2 by 2, 3 by 3, and all that. And then once you actually, I would request you to take this as a problem, as a homework, and try and find out, without Googling, of course, and try and find out how many squares are there, which are 2 by 2 and 3 by 3 and 4 by 4, and see if you can find a pattern there. Okay. If you can find a pattern, that will be really nice, and see how many things are there which can be a pattern. Now, what happens when such a question starts coming into a class is the process of discovery happens in a class. Okay, which brings me to the last slide, which is we start with some kind of a problem, a very, very open-ended exploratory problem. Then we ask questions around it. What do we think? Like the chessboard, right? So the problem statement is we want to find out how many squares are there in a chessboard. Okay. And then we draw a chessboard, and there might be children who have never counted the number of squares in a chessboard. So the first step is getting all the kids to one place, which is at least all of them should be sorted as far as 64 squares are concerned. And they should be adequately convinced that there are 64 squares in a chessboard. That is step number one, for the whole class to now at least agree there are 64 squares in a chessboard. Then we ask the next level of exploratory question. Okay. Then we ask the next level of exploratory question and say that, is that it, or is there some more? And as we go further and further and further, we discover and discover and discover all the way. As a teacher, we just guide and don't give away the answer. And finally, we develop that into a solution. And who owns the solution? Who found the solution? Who gave the solution? Nobody gave the solution. But do we have a solution? Yes, we have a solution. Who found the solution? The class found the solution. So who owns the solution? The class owns the solution. It is not my teacher told me so, right? So we don't want to get to a place where the formal authority of the teacher is the reason why they believe you. We don't want them to have belief in you. They might love you, that's a separate thing. You don't want them to believe you, but you want them to think for themselves. And for that, this whole thing is about building intuition and developing that process of discovery. All right. So that brings us to a close on this particular topic. We unfortunately don't have Neeraj and Namita, but we've also pretty much run out of time.
We still have 10 minutes, 12 minutes more, I guess, but
yeah.
Okay.
So if you want any questions on either on mensuration, which Sendil was talking about earlier, or on building intuition discovery process, or you can share any thoughts. It need not be questions. I mean, the whole idea is we all want to learn together. If you have any thoughts, any activities, anything you've done, and if it's a long activity, you can share it with Smita on a short email or a WhatsApp in the WhatsApp group. Then we can take it up as a case study in the next session as well. Anupama, can we get some more examples like chessboard? Oh, there are plenty, Anupama. There are plenty. I will try and share some more. Actually, you know what? Every question can be converted into something like this. Okay. So I don't. So again, when I give away saying that these are some 6, 7, 8, 9 questions which we can ask for developing intuition and discovery, what I'm also doing simultaneously, Anupama, is I'm stopping the discovery process for you. Okay, so we have to be careful in doing that. We should not do it with anyone. I'm not saying in a way. So we all want to learn it and understand it correctly. It is not that I don't want to share it. There are plenty of examples, and don't Google it. But my request is just take any problem you have and try and see whether we can create it into an exploratory problem. Any problem. Okay. So without so I'll give you a small one on science, right? The earth is round or the earth is flat? Anupama, is it a sphere or is it flat? Once I told her I won't give anything, she went off it. It's a sphere. How do you know? You can speak up also, Anupama, if you like. How do you know it's a sphere? Theory. Somebody told you. So it's a faith-based science is what we have. Right? So what is it? Is it science? Is it a process of thinking which we have deployed to understand that the earth is unlikely to be, at least can we think about enough to get to a conviction? It is very unlikely that it is flat. Okay, there are some things we can do. If we take a long trip, we go to the other end of the world and then come back around, and we know that we have completed a circle. Okay, yeah, not exactly sphere, Lata. I'm not getting to that right now. Not exactly sphere. That is fair enough. The larger point I was trying to make is that when we say that the Earth is round or spherical, what we have done is basically our teacher told us so, and we all believe it. Okay, that is the larger point I'm driving, that as far as I can see through my observation, it is flat. Okay, but I somehow believed it. Now in math, we don't want our children to believe that the volume of a cone is equal to 1 by 3 pi r squared h or something like that. We want them to find out. You don't take it from me because I'm telling you so. Let us explore and find it together. When we explore and find it together, all the simple thing which happens is there is cognitive struggle which the children go through. The process of discovery happens as a class. The ownership of that particular discovery belongs to the class. It is no longer my teacher told me so. It is no longer about that. It is just that I found it. How do you know? Because we found it as a class. Imagine the kind of pride and the confidence and the true self-confidence which will come in a child if the child just discovers all these things. Now, the next time around, when you say, what is the volume of a cuboid? You're not going to get paralyzed and say, oh my God, I know this formula, but I can't get it now. I can't get that formula. I know it. I know this. It's no longer that. Oh, it's a cuboid, right? Okay, cuboid, it is a base and it's just going vertically, which means a little bit of base stacking is there. So once I know what will be the area of a base, now you don't take a cuboid and you make an irregular, like a tree trunk, which is a bit irregular. It's not an exact circle, let us say, a tree trunk. And then it is, but somehow magically it is going perfectly up. Okay, what will be the volume of a tree trunk like that? Then we will know that is the base, whatever the amorphous base is. How do we know what is the area of a base? It's a very wiggly line, right? It's an amorphous wiggly line. But at least we will be able to place it on a graph paper and count the number of squares, or, larger than half we can count. So it will build intuition. So that's all I'm driving at. So Lata, your point is valid, but that was not my point, whether it is sphere and all that. Again, how do we know it is not an exact sphere? The question is valid. Okay, because somebody told us it's not an exact sphere. How much is the tilt in Earth? We'll say 23.5 degrees. Why? Because my teacher told me so. Is the earth going around the sun or sun going around the earth? I mean, are you kidding me? Every day the sun is rising in the east and going to the west. I can see it with my open eyes. I can see it happening. And you tell me that the earth is going around the sun? Are you kidding me? How do we know? So many of the facts in science or in life, we have just taken it for granted. We don't want our children to go through that. We want them to just explore and discover for that. There are certain things we finally have to push it down their throat. But I'm not saying, not being idealistic and saying 100% of it. But at least let's not get down to formulas way too quickly. And that's my only appeal. Okie dokie. We will then bring the session to a close if there are no more questions. So we'll add 6 minutes to the next session. Okay.
Does anyone have any questions? I think someone's speaking up. Cannot see who.
Okay, now everyone has gone on mute. If someone is speaking, then you will have to unmute.
Does anyone have any questions to ask?
No.
No.
Radio silence.
That was an amazing session.
Yeah.
Thanks, Ramesh, Senthil and Bama. Amazing session. Eye-opening for many, I'm sure. Please do share your feedback. Thanks, everyone, for attending the session. And I'll just send the...
Oh, we lost your voice, Smita. You're gone on mute. I'll just send, and that's where we lost you.
Okay. I was just saying thanks everyone for joining the session. The session was amazing, and do share your feedback. And if there's anything, just let me know. I can help you out. Thank you. I think we can end the session.
Thank you,
Okay,
Smita.
super.
Thank you.
Thank you,
Bye.
Smita.
Bye.
Thank you, everyone. Bye.